So the next one is we will discuss about coplanar equilibrium equations to solve or analyze equilibrium problems in coplanar force or coplanar equilibrium analysis. So in this section, we will discuss the possible equilibrium equations in the analysis of single bodies. So these equations will depend on what type of force system that we are going to solve based on the problem. So in general, we have three coplanar force system. We have general coplanar force system, concurrent force system, and parallel force system. So let's start first with general coplanar force system. So there are three common equations we can use. We have the summation forces x equals 0, summation forces y equals 0, and summation moment at any point or arbitrary point is equal to 0. Take note that point O is an arbitrary point lying on the xy plane, so it may be any point in the system. So, but in other different cases, there is some ways we can solve a general coplanar force system. So we have summation of forces F at x prime axis and y prime axis equals 0, where x prime and y prime are any two non-parallel and not necessarily perpendicular directions, and point O is an arbitrary point. So in some cases where problems are forces that are more convenient to solve in a different axis, shall we say an inclined axis, so this method is sometimes used. Next is we can have two moment equations and one summation or one force equation. So it is possible to replace one force equation with another moment equation. So next is the other one is three moment equation. So you can use three moment equations, and you can replace the two force equation with the other two moment equation. So these are the possible equations you can use. Next is for concurrent force system. Obviously, we already know that for concurrent force system, we can use two force equations because there will be no possible moment equations that we can use because all forces are concurrent to a common point. Then for we can also use two moment equations where A and B are any 2 points on the xy plane except for the point O, provided that A, B, and O are not collinear. Then we have one force equation and one moment equation where A is any point in the xy plane and x prime is any direction that is not perpendicular to the line connecting points O and A. So in parallel force system, we have one force equation and one moment equation. And we can also use two moment equations for parallel force system. So this is where we will try to solve now the problems involving single body problems in equilibrium analysis for coplanar force system. So these are the steps. The first one is we draw the free body diagram of the body. Next is we will write the equilibrium equations that we can use in the problem. And next is solve the equilibrium equations for the unknowns. So first is, we have here the homogeneous 60 kg disc supported by a rope AB rests against a rough vertical wall. So determine the tension in the rope and the reaction at the wall. So as we can see here, we have a disc which has a given weight, which is the active force. So basically the weight is acting at the center of the disc. So this is 60 times 9.81. Then we have the tension in the rope, which is this one. And we have here the normal force and since it is a, shall we say, a rough surface, meaning it's a friction surface, so meaning there will be a friction force. Remember that the direction of the normal and the friction force is not yet, or shall we say in the friction force not yet final, because we don't know if we have the correct assumption. So the tension is, we have a slope here. So this is 200 over 150. So basically 200 over 150 is 4 over 3. That is a 345 triangle. So what will happen is, we have like this. So this one. So how to solve this one? So to solve this, we can start first by solving FC. We take advantage. We will take advantage that there are 3 unknown forces, but the 2 forces here, 2 unknown forces is intersecting at point B. So we can do summation moment at B equals 0 so that these 2 forces is not included. Then we will only have 1 unknown forces. So we have here the weight of the disc, and we have the slope. So this is what I'm saying. We can start with summing up moment at B to take advantage that the 2 unknowns NC and T is acting at B. So that we cannot include these 2 forces by summing up moments at B. So to do that, summation moment B equals 0. Actually, if we sum up moment B equals 0, we only have 1 force. We have FC. Distance is 150. Negative, because we will have counterclockwise positive. FC is clockwise at point B. So we have no other forces. So what will happen is FC is 0. We don't have a friction force. So calculating FC, we have FC equals 0. Next, if we don't have the values of FC, we can now, which is this one, we can now solve the other 2 forces, which is NC and T. We can start with summation forces Y, because we can solve for T there, because NC will not be included because it is in the X direction. So we can sum up forces at Y. So we have FC plus 4/5 of T minus 588.6. So we know FC is 0. We can get value of T, which is 735.8. So take note of the sign conventions. We have negative for the weight because it is downward in the positive y-axis. Then we have positive for 4/5 T because it is upward. Then since we already got T, we can now solve NC by summation forces X, going right positive. So we have positive for NC, it's going to the right, and negative 3/5 for T because it is going to the left. So substituting the value of T here in the equation, we will get NC equals 441 newtons. So the answers are, we have T equals 735.8 newtons, and the frictional and normal force at the wall is 0 and 441 newtons respectively. Next is, for the given figure below, a distributed load due to water pressure is acting on the upstream side of the flood barrier. Determine the magnitude, the support reactions at the pin support at A. We have a pin support at A here, and a roller support at B. Neglect the weight of the barrier. So we will not include the weight of the barrier. So the only active force is the pressure, which is a triangular load. Pressure due to the water pressure. So which is 3,200 pounds per foot. So first thing to do is we will draw the free body diagram. So we know that we have for the reactions, we have AY and AX. Then for the normal force, we have this one right here, normal at B. So that is 60 degrees. The horizontal, or you can use this one, which is 30 degrees. So depending on your preference. Then this one right here, the triangular load, the resultant there is the area of the triangle, which is 1/2 base times height, or 10 feet, times 3,200 pounds per feet. So the resultant there is 16,000 pounds. The location will be 10 over 3 or 1/3 of 3. The other one right here is 2/3 of 10 or 20 over 3 feet. So, whichever is used. So, this will be the free body diagram. So, this is 90 degrees right here. Because this is 30 again. So, all in all, we have 90. This one right here is 90 degrees. This one. So, we have R and the location of R. So, the first thing we do is, since we have three unknowns, NB, AX, and AY, we can calculate NB by summing up moment at A, taking advantage that the two forces here is intersecting at point A. So, if we sum up moment A, we will not include these two forces in the equation at summation moment A. So, you will not see AX and AY there. So, we have 16,000 times 10 over 3. That is positive because that is counterclockwise because this is going here, this direction. Then we have NB. At point A is clockwise, so that is negative NB times 8. So, you will get NB 6,666.67 pounds. Then after that, we can now calculate for summation forces Y and summation forces X. So, I use this angle right here. So, we have two angles here. We have 60 degrees and we have 30 degrees. So, I use the 30-degree angle. So, if we use summation forces Y, we have two forces, the AY and NB. So, both are positive because both are going upwards. So, we have AY positive, NB sine 30 equals 0. So, we get a negative answer. AY equals negative 3,333.33 pounds. Meaning, we have a wrong assumption in the direction of AY. Meaning, the final answer here must be going downward. So, this is the correct answer. So, for AX, we have summation forces X equals 0, going to the right positive. AX is positive because it is going to the right. NB is positive also because it's going to the right. NB cosine 30. 16,000 is negative because it is going to the left. So, AX is positive, meaning this is correct, going to the right. Because we got a positive answer, meaning your assumption that AX is going to the right is correct. AY, the assumption for AY is not correct because we assume upward direction. So, the assumed direction of AX and NB is correct since the resulting answer is positive. In the case of AY, where the result is negative, the correct direction will be opposite to the direction presented in the FBD. That's why the answer will be downward. And for AX and NB, since it is positive, we will get the same direction from the FBD. Next is determine the mass of the heaviest uniform bar that can be supported in the position shown in the figure. The breaking strength of the horizontal cable attached at C is 15 kilonewtons. So, meaning in this part of the problem is that if the tension in this cable reaches 15 kilonewton, basically it will break. So, this will break. So, what will happen is if the cable breaks, the rod will slide in this direction. This point right here will go downward, and this point right here will go downward because we will not have this cable anymore because it will break. The question is determine the heaviest bar that can be supported so that the rod here will not break or on the verge of breaking. So the heaviest bar will occur if the tension in this cable will reach its maximum because the heavier the bar, the tension in this cable will also increase. Because if the bar is heavy, the tendency is the bar will move in this direction such that it will increase the tension in this cable. It will try to pull this cable. So, to do that, let's create a free body diagram. So, the free body diagram is like this. So we have here the weight of the bar, which is unknown, the tension. So to make it the heaviest possible bar, we will need to use the maximum value of the tension force, which is 15 kilonewtons. Then we have the normal reaction at A. So we will change the slope. It will be 4 in the horizontal and 3 in the vertical because it is forming a 90-degree angle. Then we have the normal reaction at B. This is the normal reaction at A. So it will look like this. So again, 4 horizontal, 3 vertical. So this one right here, 4 horizontal, 3 vertical. So to do that, the weight W of the heaviest bar can be obtained when the tension T is set to its maximum limiting force. Again, that's what I said earlier. A heavier bar would result to a tension in the cable greater than 15 kilonewton where it could break. So if we try to use a value greater than 15 kilonewton, which is not possible, it will break. Therefore, the weight that you will also get there is greater than the heaviest bar. So therefore, we will obtain the heaviest possible bar without breaking the cable if we reach the maximum limiting force of the cable itself. So the direction of the two normal force is perpendicular to the surface, which is I already indicated in the problem. So there are 3 unknowns. So we can start solving for the unknown forces. To take advantage that the 3 unknowns NA, W, and NB, take advantage that W and NB is directed in the positive y-axis. So if we use the other equation, which is summation forces x equals 0, these two right here will not be included in the solution. So we will we can solve now NA. So summation forces x equals 0. We have, going to the right for NA, that is 4/5 of NA. Then going to the left for the tension force, which is negative 15. So we will get NA. Next one is, using the value of NA, we can now solve for W. By the way, what is being asked in the problem here is we solve the mass of the bar. The mass of the bar will depend on the weight because it is mass over gravity. So the mass is equals to weight over gravity. So our target here is to get W. If we already get W, that is the only way we can get the mass. So it doesn't mean that we need to solve the other reactions because it is not asked in the problem. So if you include that in the solution, it's still okay, but it is easier that you can find a way to solve W in the fastest way possible, wherein there's no need to solve for the other reactions. So in this case, we will only solve for NA. And after solving NA using this summation forces x0, we can now try to solve W by summing up forces moment at B. Because if we sum up moment at B, what will be included is only NA, T, and W, because NB is intersecting at B. So we already got the value of NA from this equation. Now we can now solve for the other unknown, which is W. So to do that, summation moment B equals 0, counterclockwise positive. So what will happen is we break down this into components, especially NA. Let's start with W. W at point B is counterclockwise. But the distance is this distance right here. So this is 1.2 cosine 20. So what will happen is we have W times 1.2 cosine 20. That is the force and the distance. With A, since this is downward and B is on the right of W, so it is counterclockwise. Next is 15 kilonewton force. So this is 15 kilonewton force. This is the distance right here. This is the distance. That distance is the same with this distance. So this distance is 1.2 sine 20. T is counterclockwise at point B, so that is positive also. 15 times 1.2 sine 20. So that is the force and the distance. Force and the distance. Next, we will break down this NA into two forces. We have 4/5 NA and we have 3/5 NA. So, let's start first with 3/5 NA. 3/5 NA has a distance which is this one. This is the distance here. And its effect is clockwise because it is upward and B is on the right, so it will go like this. This rotation at point B. So the distance here is this distance, 2.4, which is also equal to this distance, 2.4 cosine 20. So that is negative because it is clockwise. 3/5 NA, the force, and the distance is 2.4 cosine 20. The other one, 4/5 NA, is the same, which has a clockwise effect, but the distance is, actually this is the distance, which is this one. That is 2.4 sine 20, because if we look at this triangle right here, this one, so the height of the triangle is 2.4 sine 20. So negative because it is clockwise. The force is 4/5 NA and the distance is 2.4 sine 20. So we can apply that summation moment at B equals 0. So we will get a value of weight equals 28 kilonewtons. So since what is asked is the mass, we can get the mass by converting the weight into newtons, and which is 28 kilonewtons to newtons, then divide it to the gravity, 9.81 meters per second squared. So we will get 2.854 kilograms. Or shall we say 2,854 kilograms. So that is the final answer. Let us have here our last problem. So for the given frame shown, the given figure supports a part of the roof of a small building. Knowing that the tension in the cable is 150 kilonewton, determine the reaction at a fixed end at E. So this is a fixed support here. And we have a cable attached at D. Neglect the weight of the frame. First thing is we create the free body diagram. So we have here the tension in the cable, which is 150. Away from the body, which is the frame itself. Then we have the reaction, EY, EX, and couple at E. Or shall we say moment at E. Or couple at E. So it will look like this. So we have the tension in the cable. We can use a slope here which is 6 and 4.5. So that is 3 and 4. Because 4.5 over 6 is 3 over 4. Then that's it. Next is after drawing the free body diagram, we can now solve for the three unknowns, which is EX, EY, and ME. So let's start first with EX. EX is quite easy because we have EX going to the right positive. And this one right here is 3, 4, 5. So we have 3/5 of 150 positive going to the right. So we will get an answer of EX equals negative 90. Since we get a negative value, meaning this is the opposite of the direction is the correct answer. So meaning the correct direction is this one. So this is supposed to be EX going to the left. Then we have summation forces Y. We have EY upward, the only upward force. Then the other ones are negative. We have 4 downward forces, which is negative 20. So we have negative 24 forces. And we have 150 newtons going, kilonewtons, which is going downward. So that is vertical component, which is 4/5 of 150. So since we get a positive answer, so meaning that we have the correct assumption of the direction of EY. So EY is 200 kilonewtons upward. The last one is the moment at E, or the couple reaction at E. So moment at E equals 0, counterclockwise positive. So let's start first with the moment E, which is, we assume already that it is counterclockwise. So that is positive. Then we have all the forces here, which is these 4 forces are counterclockwise at E. So we will use a positive value of all the 4 forces. But we have different distances. Example, for this 20 kilonewtons force, the distance is this one, which is 7.2 meters. For this 20 kilonewton force, the distance is this one, which is 5.4. The other one, 20, is this one, which is 3.6. And the last one is this distance, which is 1.8. So that will be the moments with respect to the vertical forces, which is 20 kilonewton. All are positive. The last one is this one. So we have, this is, I believe this is 4 and 3. So this is 4/5 of 150. And this is 3/5 of 150. 3/5 of 150 is not included because it is passing through point E. So we will only include 4/5 of 150, which is a distance of 4.5 meters. It is negative because the effect is clockwise. As you can see, this is downward and its rotation on point E is clockwise. So that is 180 kilonewton meter. So since the answer is positive, therefore we have the correct direction, which is ME is counterclockwise. So the answer is this one. So now let's have some practice problems. So that you try to solve these problems on your own and check if you get the correct answer afterwards. So we have here a 30-pound homogeneous bar AB supports the 60-pound block. The end of the bar rests on frictionless inclines. Determine the distance x for which the bar will be in equilibrium in the position shown. So the answer to this problem is x equals 10.5 feet. So for our next problem, the beam is subjected to the 3 external loads shown. Compute the reactions at the support point O, and the xy plane is vertical. So as you can see, point O, there is a fixed or built-in cantilever support. So the answer to this problem is next is we have determine the angle theta for which the 1250 Newton homogeneous cylinder will be in equilibrium in the position shown. Also find the tension in the rope AB. The answer to this problem is last problem. Determine the horizontal and vertical components of the reaction at the supports, neglecting the thickness of the beam. The answer to this problem is so thank you for listening to this video. Make sure to like and subscribe for more videos to come.